In the previous video we started looking at oscillations. We're going to now look at describing that periodic motion in terms of some of the quantities that are important. Again, we're going to look at a graph in order to quantify some of these aspects. So we've got that periodic function again, so increasing and decreasing over time. So on the horizontal axis we're dealing with time, and on the vertical axis we're dealing with the position or the displacement. So position x time t. Now we're basically going to look at certain parts of the oscillation and identify particular aspects that we can actually quantify. But before we do, we need to refer to this particular line here. That's the I'm going to label that here, and then we'll write a definition underneath. That's known as the equilibrium position. Now that applies to both oscillations and also applies to waves, so it's a term that you need to be comfortable with and familiar with. So if you need to jot down the definition and make sure that you understand the full detail behind it, make sure you do that. Ask me questions if you need to. So equilibrium position is basically the point at which all forces are balanced. So it doesn't matter whether the object is actually moving or not. It's the point there where all forces on the object are balanced. The other easy way to think of it is it's the point at which the object is actually at rest. I didn't want to write that as a definition though, because the object can be moving through the equilibrium position and it's not at rest. So a more technically correct definition there is that it's the point at which all forces on the object are balanced. Now the other quantities that we need to deal with are, I'll just change colour here to make it a bit clearer to see what we're labelling. So the first one is this one here, that's going to be our value x naught. Now that is the amplitude. So amplitude is simply, think of it as being how tall or how big the oscillation is. So x naught is the maximum displacement of the object from its equilibrium position. Again, this idea applies to waves as well, and we'll talk there about what happens with peaks and troughs or with compressions and rarefactions. But for the purposes of considering an oscillation, it's just the maximum displacement from the equilibrium position. The next quantity then is the period. So if we look at the period, we're really dealing with any 2 points on this graph that are in phase or doing the same thing. So these 2 points that were sort of right at the top of the sine wave, we could have chosen, say, this point here and gone across to this point here, because they're both on that sort of downward slope of the graph. Likewise, we could have chosen this point and this one, so it doesn't really matter which 2 points you choose, so long as they're at the same part of the oscillation. So the period relates to the amount of time. So period is simply the time taken for one complete oscillation. The next quantity then is not one that we can actually show on the graph, but it's one that relates directly to the period, and that's the frequency. And we use the letter F there to represent frequency. Frequency is the number of oscillations that occur in 1 second, or the number of oscillations completed in 1 second. Frequency can be stated in other units, so it doesn't have to always be per second, but when we get back to SI units, it's going to be in 1 second. Now, that means that we've got this fairly straightforward relationship. If you think about period, it's the time taken for one full oscillation. Frequency is then the opposite of that, the number of oscillations completed in 1 second. So we've got a relationship here that the period is equal to 1 on f. So a nice easy calculation there. It's in the data booklet, so highlighting it there, but the relationship there between frequency and period. Important to note here too that when period is in seconds, then frequency is in hertz. That's named after a scientist, so hence the capital H, spelled Hertz if you want to write the units. Per second is the same as hertz, in other words. So there's some of the basic quantities to do with periodic motion. There are a few others that we'll need to get onto when we get onto wave motion, but we'll deal with that in a later subtopic.